Hi chemistry students, if you are looking for the vodcast trends on the periodic table, you have come to the right place. In this vodcast I'm going to walk you through 3 ways that we can use the periodic table as kind of a cheat sheet. As long as you understand how to use it, there's not much you have to memorize. So the 3 things we are going to learn here is how many valence electrons does each element on the periodic table have. Well, almost each element. The transition elements get a little funny. So we're going to learn to draw something called a Lewis dot structure. We'll also talk about the size of the atoms, also known as the atomic radius, and then we'll be talking about what ionization energy is and how we can find that on the periodic table. So here we go. Let's start off with Lewis dot structures. Here's our good friend, the periodic table. You already know something about it. And then these funny looking diagrams down here should look familiar to you. These are very simplistic Bohr models of the atoms. We have the positive nucleus here in the middle with those protons and neutrons, and then there are different energy levels. There's energy level 1, energy level 2, and these are where electrons are found. Now we already know that the Bohr model is very simplistic and not the greatest way to describe how electrons actually travel in that electron cloud, but its simplicity makes it useful for drawing Lewis dot structures. So here is what a very basic structure, a very basic picture of what lithium looks like. So it has 2 electrons in its first energy level and 1 in its second energy level, a total of 3 electrons. Remember, we can find that up here on the periodic table. That atomic number of 3 tells us it has 3 electrons. We can do the same thing with oxygen. It has 8 electrons total, so 2 in the first energy level, and then 6 in the next energy level. You'll notice that I have some paired up and some are on their own. That's kind of what electrons tend to do. We'll talk more about that in a little bit. Here's beryllium right here on the periodic table, 4 electrons, 2 in the first energy level, 2 in the second energy level, and then there is neon with a total of 10 electrons. Okay, the electrons we're going to pay very close attention to from here on out in chemistry are the outermost ones, the ones in the outermost energy level. So for lithium, here is its 1 valence electron. For oxygen, it has 1, 2, 3, 4, 5, 6 valence electrons. Beryllium has 2 valence electrons, and neon has 8. You'll find out that 8 valence electrons is kind of a magical number for elements. So valence electrons are electrons in the outermost energy level. And you'll have to know, by looking at an atom, how many valence electrons it has. And that seems a little scary because you think, oh no, am I going to have to draw one of these big pictures for every element on the periodic table, like iodine or mercury? Those are big elements. And the answer is absolutely not. If you know the cheat sheet, if you know how to use the periodic table, then you don't have to memorize anything really, or very little. The Lewis dot structures, if you need to know how many valence electrons elements have, their place on the periodic table up here will tell you. So first of all, though, let's take these pictures right here of these elements and let's turn them into Lewis dot structures. Rather than draw all these out, scientists use a Lewis dot structure, and here are the rules. 1 dot represents 1 valence electron, and you write the symbol of the element and you place 1 dot at a time around the element symbol, pairing them up only if needed. So for example, lithium has 1 valence electron here. You can see it right here. So I just put 1 dot off to the side of lithium. I don't really care which side you put the dot on. Usually scientists start on the right-hand side, but as long as you get that 1 dot somewhere around there. Pretend that lithium is in a box right here, and on one side of the box you put 1 dot. Okay, this is what we call the Lewis dot structure for lithium. Way easier than drawing all of this out. Mrs. Dorn, what about these 2 electrons right here? Did they disappear? No, we just don't care about them. Valence electrons are special. The Lewis dot structure only shows the valence electrons. Okay, I understand still that lithium has 3 electrons total. I'm only concerned about putting a dot for its 1 valence electron down here, though. Same thing with oxygen. I write the symbol for oxygen. Oxygen has 1, 2, 3, 4, 5, 6 valence electrons, so I just place them around. I go 1, 2, 3, 4, 5, 6. I left these unpaired. They don't pair up unless they have to. Again, think of this as like a box around oxygen with 4 sides. Put 1 at a time, pairing up only if you need to. Beryllium has 2 valence electrons, so I take beryllium, Be, there's its symbol, and I put 1 dot there and 1 dot there. Again, I don't really care which side they're on, but don't pair them up unless you have to. Neon, we had to pair them up. It has 8 valence electrons, so I put 1, 2, 3, 4 on there, and then I had to go 5, 6, 7, 8. 8 valence electrons around neon. Okay, so don't forget the rules. One dot represents one valence electron, and you put one dot at a time around each of the 4 sides, pairing them up only if needed. Okay, so you should be able to look at the periodic table and very quickly tell what the Lewis dot structure of an element is going to look like, because everything in this first column here only has one valence electron. If you don't believe me, start drawing pictures of them out, kind of like these up here, and you'll start seeing the trend. Or you could just trust me. Everything in this group right here has one valence electron. Everything in this group right here is 2 valence electrons, so all of the Lewis dot structures are going to look very similar like that. I'm skipping over the transition elements because those guys get really big. They have some extra energy levels buried in there. They have varied numbers of valence electrons, which makes them really useful in society because they can be used in a lot of ways thanks to kind of their shifting valence electrons. So let's just forget these guys for now. Trust me, go along with it. Everything, I say everything as we get down here, some funny things start to happen, but for our purposes, everything in this group has 3 valence electrons. Everything in this group has 4. See how that structure looks? Okay, I had to move this guy up here so you can kind of see it a little bit better, but everything in nitrogen's group has 5 valence electrons. Oxygen's group has 6, 7, and everything in the noble gases has 8 valence electrons, except little helium only has 2. Yeah, because it's such a little atom. What about the lanthanides and actinides? Again, remember, they belong up here in the periodic table, so they have funky numbers of valence electrons. But if you can remember this pattern on the periodic table, 1, 2, 3, 4, 5, 6, 7, 8, okay, that's how many dots you put around your element symbol to make a Lewis dot structure. Let's see if you understand it. Let's practice. I want you to draw the Lewis structure for these 3 elements. So you can hit the pause right now and give it a try. I'm going to go ahead and start to work with this a little bit. The marker grabbed up here. Magnesium is in the second column right here, so everything in that column looks like this. 2 valence electrons. There's a Lewis dot structure for magnesium. Silicon right here. Everything in this group, remember, has 4 valence electrons. I'm going to put 1 on each side. Those electrons repel each other. They don't like to be close to each other, so we try to represent that in our Lewis dot structure. These are kind of messy. You can live with it though. There we go. There's what silicon's Lewis dot structure looks like. And last but not least, iodine is one of our halogens. Highly reactive. Everything in there is, because they have 7 valence electrons. So I'm going to put 7 little dots there. That's much neater. Look at me go. That is how the Lewis dot structures look for those elements. So that's one trend you need to understand on the periodic table. As you move from left to right, the number of valence electrons increases by 1. Transition metals, some varied trends in there. Okay. Pay attention to those valence electrons. They're going to come in handy when we start learning more about chemical reactions. Moving on. Other trends on the periodic table. Atomic radius. Radius is the distance of half a circle or halfway across a circle. So in chemistry, it's the distance from the nucleus of an atom to the edge of its electron cloud. So right in the center to the edge of its cloud. Atomic radius is a really tiny number, and electrons are moving all the time, so it's kind of an average, but you get the idea of what atomic radius is. Take a look at the periodic table here that shows the relative sizes of the atoms, and you can kind of start to see the trend for yourself. This is a nice model. As you move from left to right across the periodic table, you'll notice that atoms tend to get smaller in size, which is weird because you think, well, you're adding protons, you're adding electrons, wouldn't they get bigger? But as you move from left to right, the radius decreases because that nucleus, that central part, is so strong. It's getting more and more protons, and the protons are the attractive force that pull those electrons in. So lithium doesn't have a very strong nucleus, so it doesn't pull its outermost electrons in very tightly. Fluorine, though, has way more protons in its nucleus, and it hugs those electrons in tighter. That's the case as we move from left to right across the periodic table. Yeah, the noble gases do something kind of different there, but that's the general trend. As you move from top to bottom, though, those elements do get bigger because you're adding extra energy levels. Lithium only has 2 energy levels. Cesium has way more energy levels. It has way more electrons. And the layers, those electron levels, those energy levels, shield the outermost electrons from the attractive nucleus. So this picture down here kind of shows that. If you have a nucleus right here, they labeled it Z. Here's your first energy level with these little electrons, and they're attracted to the nucleus. And so are these electrons out here. But this first layer of electrons, remember, charges that are alike will repel each other. So this electron and that electron and that electron, they're all repelling each other. So they're kind of keeping those outer electrons from getting too close to the nucleus. So as you move down the periodic table, these atoms are getting bigger because of that shielding effect. We're adding energy levels and they're shielding those outermost electrons from getting too snuggled into the nucleus. So that's the trend on the periodic table in terms of atomic radius. Ionization energy is the amount of energy needed to steal an electron from an atom, thus making it a positive ion. Why do atoms steal electrons from each other? Because they're kind of jerks. And we'll talk more about that later. But to kind of show you the process, when an electron gets released or stolen, energy is needed to do that. So you can see the trend here on the periodic table. There's ionization energy. They cut out the transition elements. You won't see them, but here's our regular periodic table. They kind of made it 3D right here. And as you can see, as you move down the periodic table in each group, that ionization energy decreases. As you move from left to right, it tends to increase. In other words, it takes a lot of energy to steal electrons from these guys, but not so much energy to steal electrons from these guys. Why does that happen? As you move from left to right, that ionization energy increases because the nucleus is getting so strong as you move from left to right. It's really hugging those electrons close. But as you move from top to bottom, that shielding effect of all those extra layers keeps that nucleus from hugging those electrons too closely. So if I was going to take that information and put it onto my periodic table, first of all, make sure that you have a periodic table and that you've written this trend on it for Lewis dot structures. That's really important. It'd be an easy thing to put onto your periodic table. Nice visual. And then take the same periodic table or a different one and make sure that you get the trends for radius and ionization energy written on there. And I found the easiest way to do it is I drew an arrow going this way and then this way. And it reminds me as I move this way and down on the periodic table, elements get bigger and bigger, their size increases, but their ionization energy decreases. So if you can kind of remember this little pattern right here, you'll be okay. Another way that you can remember it is FR down here. I think of it as the biggest loser. It's got a really, really big size because it's in the lower left-hand corner, and size increases as you go to the left and down. And so that's why I'm saying it's the biggest. I'm also saying it's the biggest loser of electrons because ionization energy decreases as you move to the left and down the periodic table. So francium does, it easily loses its electrons. It has a very low ionization energy. So if you can kind of get this drawn on your periodic table and write yourself a little clue about FR, call it the biggest loser, and that'll help you remember it. All right, that is the vodcast for trends on the periodic table. This should help you as you start working on ChemQuest 14, 16, and 17.